Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I've been guiding you through the chemistry course. In this lesson we'll be looking at chemical equilibrium, and we'll look at it under the topics. Equilibrium systems, we'll look at equilibrium in reversible reactions. We'll look at the Le Chatelier's principle. We'll look at the equilibrium constants and free energy and electrode potential once again, and then consider the hydrolysis of salts and indicators. Alright, let's start it. So when we talk about equilibrium simply means a balance. It's a balanced system. A balanced system. And when we talk about an equilibrium system, it means a system where there is a balance. There is an input, there's an output, and there is a steady balance maintained between the input and the output. So, like we have this description of two children playing on a seesaw. Of course, one of them goes down, the other one comes up, and all of that. But at a particular point in time, of course, if you balance them rightly, you have the point where the seesaw will actually be horizontal. One may be sitting on the edge while the other is sitting closer to the middle or something like that. But you can achieve equilibrium. Now, equilibrium systems are usually sought after when you are working with chemical reactions that are reversible. Reversible reactions, where you have reversible reactions, to look for a particular point in which that reversible reaction is at equilibrium. It is the point at which the forward reaction is equal to the backward reaction. Therefore, there is no change in reaction. That is, there is no change of substance. There is no chemical reaction being noticed. So the number of products available equals to the number of reactants available, or rather, the number of products available, yes, equals the amount of products available is equal to an amount of reactants also available. Every time the reactant changes, they form new products, and the products also change immediately to form new reactants, balancing out the effect of the original change. So we have chemical equations such as so let's take this particular reaction. We have calcium trioxocarbonate 4. It decomposes in the presence of heat. Imagine that our calcium trioxocarbonate 4 is inside a vessel and I have a lid over it. So this is the calcium trioxocarbonate 4. As we are heating it, particles of carbon dioxide would fill the entire place. And as well as the particles of carbon dioxide are going up, as they're trying to escape, since they cannot escape from the system, then they kind of like fall back and react again with the calcium oxide and produce the calcium trioxocarbonate 4. No matter how long I keep this reaction going, so long as I'm not taking out one of it from the system, we will still keep having it going forward and backward. There will be production of calcium carbonate and carbon dioxide, and there will also be production of the calcium oxide, calcium 2 oxide, and carbon dioxide, and there will also be production of calcium trioxocarbonate 4 on the other side. So it will be balancing out. As this one is rising, when it rises and it gets to this top region, it is cooled to a certain temperature. The reaction between the calcium particles occur, and then it falls back as calcium trioxocarbonate. So that's what happens in a closed system. Yes, we have two different types of systems that we can have. We can have an open system, we can have a closed system. An open system will be one such that I have this kind of reaction, and probably I even have it covered sort of, but I take out my gas into a particular, let's say, can. I collect my gas out. In this particular case, when the gas is being produced, it will be a forward reaction. There will be no reversibility because the gas is not mandated to stay. The gas will only simply go out. And of course, if I should remove the cover completely, the gas would also escape completely. So this is how it works in a particular reversible reaction. For equilibrium, when it gets to a particular point in time, the rate at which the forward reaction is happening will be the same rate at which the backward reaction is happening. And at that particular point in time, we say we have attained the equilibrium. So at that particular point in time, you will notice that there will be no more production, or there will be no changes in mass. There will be no observable changes in mass. The amount of this produced is also the same amount of this produced. The reactant and the product will seem to balance out each other. That's why we're talking about the equilibrium in reversible reactions. All right. So we've talked about the systems of equilibrium systems, and we looked at the reversible reaction system. Of course, let me re-emphasize this. This is a closed system. So as the carbon trioxocarbonate 4 is being decomposed, since the gas cannot escape, it mixes back with the product which is supposed to stay, and it forms back the original reactant. But in this particular system, which is an open system, the gas is escaping out of the components. So the products that will be left here would be calcium oxide, calcium 2 oxide. Alright, in a few seconds, some questions will be displayed on your screen to test your understanding of what has been taught in this lesson so far. Please do well by answering them, and in a few, we'll get back to you. So, welcome back. We've looked at the equilibrium systems, and we looked at equilibrium in reversible reactions. So, let's discuss one or two things. This guy, Le Chatelain, he came up with a principle. He said that if a particular chemical reaction is at equilibrium, and an external force, an external factor such as temperature, pressure, concentration, or anything like that interferes. Of course, pressure when you're working with gases. So if this thing interferes, the chemical reaction would change in such a way as to annul or to nullify the effect of that particular change. So that particular situation. So we see that he's trying to say that peradventure you have a particular reaction between hydrogen gas and oxygen gas at a very high temperature, which is leading to a very funny reversible reaction, producing steam. Now, if you compress, that is, if you increase the pressure on this particular system, if you count how many volumes we're having here, 1, 2, we're having 1, 2 volume here, we're having 2 plus 1, that's 3 volumes here, we're having 2 alone here. So if you compress the mixture, you will have the reaction falling more to this side, falling more to the steam production side than to the reactant side. And when you reduce the pressure, peradventure you reduce the pressure so that there is much more volume, you have the reaction falling more to this side, that is the reactant side, than compared to the product side. So that is what Le Chatelain's principle states. Of course, it's kind of logical. I think you should be able to picture it, but I want you to look at it from this perspective. If this is the volume, this is the volume at which this particular reaction is balanced. This is the equilibrium point. When you have your piston driven down, obviously there is a lot more pressure acting on it, so everything inside will tend to condense. It tends to condense, favoring the forward reaction. The forward reaction is having steam. In fact, the steam might even start to liquefy. It might start to produce water. So that's favoring the forward reaction. And if we have the same container but the pressure is reduced, that is, we increase the volume. Of course, gases would like to occupy every space. So this has 3. This one would now take over and occupy as much space as possible, thereby reducing the amount of steam that will be produced in the system. So that's what Le Chatelier's principle is all about. All right, let's consider the equilibrium constants. Also, we just viewed what the pressures would look like. How about when we actually increase the temperature? When we increase the temperature of this particular system, instead of the forward reaction to be favored, we will have the backward reaction more favored. Why? Because the molecules would be in more violent motion. They will be bouncing off each other. But when we cool the system down, of course, our cooling the system down is also, if we consider our the general gas equation, we have, or let me use general gas equation, PV over T, and we take out the V part and we'll consider just V and T. When we cool the system, is as good as we reducing the pressure, reducing the volume. So we would have the forward reaction better favored. It's not always like this in all situations. Sometimes it might favor the backward reaction when you cool, depending on the way in which the reaction occurs. Also, there is also the effect of catalysts. The effect of catalysts. Certain catalysts improve the chances of a forward reaction over the backward reaction, while some catalysts do actually have no effect. Yes, some catalysts, in fact, most catalysts do have no effect on this kind of reactions. Why? Because the rate at which they enhance the forward reaction is also the rate at which they enhance the backward reaction. But certain catalysts actually do allow a better forward or a better backward reaction, depending on which is desired. And also concentration. If we increase the concentration of all of one side of the expression, peradventure we increase the concentration of the steam by injecting more steam into the system, we would end up having the backward reaction favored. If we introduce more hydrogen and oxygen, we'll have the forward reaction better favored. So introducing any of these constants, any of these things, altering any of these conditions would actually have an effect on the system, and the system will always adjust to nullify or to cancel out the effect of the newly introduced constraint. So in a particular reaction, the amount of energy when something is altered, that is either the concentration, the pressure, the temperature, is altered. When something is altered, the system adjusts itself such that it cancels out what is altered. So how does it get this particular energy? The energy is actually within the system already. The energy within the system, which actually do cancel out this, is simply a balanced energy within the system, and it can be expressed as G here, which is equal to minus RT ln K, where the G is the Gibbs free energy, is a free energy, R is the gas constant, T is temperature, and K is our equilibrium constant. K is our equilibrium constant. Also, each particular component has an electrode potential. This particular reaction, since it involves ions being moved, something like an electrolytic process, it involves oxidation reduction. So there's electrode potential possessed within the system, and the electrode potential can be calculated with the expression RT ln K divided by NF. RT ln K divided by NF, where N is the number of electrons and F is the Faraday's constant for electrolysis. So we can simply say our free energy equals to minus NFE. Minus NFE. With this, we can go ahead to calculate how much of free energy is within the system available for use. Now, these energies do have a lot of applications when you're looking into relating the Lachatera's principle and trying to find the relationship between equilibrium constant, the free energy, and the electrode potential. So, let's talk about what happens in the acid-base reaction. In the acid-base reaction, you mix your acid with your base, and there is something that is coming out of the whole thing. Well, the first question is, what is an acid? The acid, of course, we have discussed earlier, is a substance, a chemical substance which liberates hydrogen ion as its only positive ion. So it liberates a proton. It liberates a proton, while a base is a substance that accepts a proton. And of course, neutralization is simply the proton from the acid being interacted with the proton, being interacted with the base, which wants a proton to produce water. That's salt and water, of course. So in a kind of a system, we would have the acid something like H+, but oftentimes we don't see it as H+, we see it as H3O+. H3O+, and we have our base as OH-. So this particular component now, it comes out of there is a kind of reaction that occurs to try to balance out, and that's what happens while we go through the hydrolysis of salts. So let's consider the hydrolysis of salts. When we take our common salt and we put it in water, when we try to hydrolyze, that's use electrolysis, of course. Hydrolyzing our normal salts, we see something come out of it, that's NaCl, and we'll have the nitrogen, the sodium plus and the chlorine minus. So we see that this sodium forms a very strong base, and this forms a very strong acid. So what comes out of it is strong base, strong acid, and that is what comes out of our normal salt. But in the case of potassium and ethanol, you see when the substance dissociates in water, your potassium forms a strong base, but this now forms an acid, and not a strong acid, instead a weak acid. So we experience inconsistency. That's what we experience. So the balance would be shifting. So it tends to produce what is more of a basic salt when it is hydrolyzed. Of course, we also notice that in aluminum chloride, when it dissociates in water, we have our chlorine coming out fine, ready to form a strong acid, and our aluminum comes out to form a weak base. So we have a weak base, strong acid scenario. When we have also the weak acid and weak base scenario, where we come up with ethanoic acid and aluminum hydroxide. That's what comes out of this. So we see different kind of hydrolysis come up with different kinds of components, but the most stable of them all is your sodium chloride, where we have your strong acid, your strong base mixing together, and you getting your very stable salts. So all these other ones tend to give complex salts, complex solutions. Let's talk about indicators. So what are indicators? Indicators are substances which do not take part in the chemical reaction which is ongoing, but do help us to detect when the reaction has occurred or not. They are just like how do I put them now? They are like headliners, pointers to the reaction. They let us know when a reaction is occurring or when the reaction is not occurring. We see many indicators that we do have, such as methyl orange, the litmus paper, and the lots of them. So in this particular exercise, we look at, I'll mention a few which they will be displayed on your screen to show you the pH range within which they operate. the pH range within which they do operate. We have methyl orange, which shows red below 3. That's pH of 3. It shows red below it. It shows orange at 4 and yellow above 4. We have the litmus paper, which shows red below 5. Between 5 and 8 it shows purple, but anything above 8 it shows blue. And we have phenolphthalein, which is colorless below 8, very pale pink at between 8 and 10, and it turns red above 10. So all these indicators, these are just some of the indicators that we do have. We have many other different types of indicators. These indicators simply just point us to the current pH value of the reaction. So whenever we want to do an acid-base reaction, we do need an indicator to know when the acid has been converted, when the system is no longer being acidic, or when it is changing states. So it is no longer being acidic, it's now becoming basic. When it's no longer being basic, it's becoming neutral. The pH value, of course, is supposed to suggest that, and the indicator will show us based on the pH value which the substance is at the point in time. Okay, in this particular lesson, we looked at equilibrium, chemical equilibrium, and we talked about equilibrium systems. So we talked about a system that is a seesaw. We talked about the open system and the closed system, and we said equilibrium is usually found in the closed system. In the closed system, of course, equilibrium is very rampant when we have reversible reaction, and that led us talking about the Le Chatelier's principle, which says that when the condition of the body, that is a system in equilibrium, is altered in terms of the temperature, the pressure, the concentration, the system would alter. It would move such as to balance out the change, the condition initiating the change. So that led us talking about equilibrium constant and relating the equilibrium constant to the free energy and the electrode potential, where we came up with the formula that the free energy equals, the free energy G equals minus NFE, where N is number of electron, F is Faraday's constant, and E is the electrode potential. Of course, we also mentioned earlier in that G is equal to minus RT ln K, where K in this particular expression is our equilibrium constant, R is the gas constant, and T is the temperature of the system. We then went into talking about electrolysis of salts and considered the strong base salts, which is the normal salt. We considered also the weak acid strong base salt, which is the basic kind of salt. And we also considered the weak base strong acid salt, the acidic kind of salt, and we considered the weak acid weak base salts, which usually form complex salts. And then we went to talk about indicators. That indicators help us to know when reaction is occurring, when there is a change in the pH value of our system. Alright, I haven't learned about all these things. In a few, some questions will be displayed on your screen to test your understanding of what has been taught in this lesson. Please do answer them, and if any of them proves to be challenging, you can go over the video another time for clarification. Thank you.